A wildfire has just swept through the grassland. The ground is still warm. Scattered across it are roasted tubers still buried in the soil, seeds scorched on the stalk, roots baked hard beneath a layer of ash. A hungry man crouches beside one of the blackened tubers, digs it out with a stick, and breaks it open. He's eaten roots raw his entire life. This time, hunger wins over hesitation, and he tries a piece that's been sitting in the hot ash. Most people picture the discovery of cooking as a single genius moment, someone deliberately holding food over flame for the first time and immediately understanding what they'd done. That's almost certainly wrong. Cooking wasn't invented. It was noticed, accidentally, probably hundreds of times, long before anyone treated it as a deliberate technique worth repeating on purpose. Wildfires were common in the environments early humans lived in. Lightning strikes, dry seasons, natural combustion. None of that required human intervention. What required human intervention was the next step, walking into the burned aftermath and realizing the roots, tubers, and seeds caught in it weren't just scorched and ruined. They tasted different. They were softer, easier to break apart and swallow. Here's the part that changes how you should picture this. Archaeologists working at Wonderwork Cave in South Africa found burned plant material and ash deposits dating back roughly 1 million years, some of the oldest solid evidence of fire use in a controlled context. That's not campfire cooking as a daily habit yet. That's early, inconsistent, opportunistic contact with fire, likely encountered from natural sources long before humans could reliably create it themselves. Making fire and using fire are two completely different skills, separated by an enormous stretch of time. For a very long period, early humans almost certainly couldn't start a fire on their own. They could only take advantage of one that already existed, keep it alive as long as possible, and use it while it lasted. This changes the whole discovery story. Cooking likely began as opportunistic scavenging of a natural disaster's aftermath, not a controlled kitchen experiment. Now think about what that first bite of roasted root actually would have felt like, with zero context for why it tasted or behaved differently. Softer texture, different smell, easier to chew. No framework for heat breaks down cell walls and starch. Just, this is better, and I want more of it. What do you think would have convinced you faster to keep eating cooked food over raw? The taste? Or how much easier it was to actually get down? The biological case for why cooking mattered is stronger than most people realize, and it's backed by real research, not guesswork. Harvard biological anthropologist Richard Wrangham built an entire theory around this, often called the cooking hypothesis, arguing that cooked food was the key trigger that allowed human brains to grow as large as they did. The logic is direct. Cooking gelatinizes starches and breaks down tough plant fiber, making food dramatically easier to digest. Easier digestion means more usable calories extracted from the same amount of food, and more calories available for an energy-expensive organ, like the brain. There's actual experimental evidence behind this too, not just theory. A study led by researcher Rachel Carmody, working with Wrangham, fed pythons cooked versus raw food and measured their metabolic effort digesting each. The cooked version required significantly less energy to digest than the raw equivalent. Less energy spent digesting means more energy left over for everything else a body needs to do, including, in humans, feeding a brain that consumes a disproportionate share of the body's total energy budget. This connects directly to something called the expensive tissue hypothesis, first proposed by researchers Leslie Aiello and Peter Wheeler in 1995. The idea is straightforward. A large brain is metabolically expensive to maintain, and something else in the body had to shrink to free up that energy. Their research pointed to the digestive tract. Human intestines are notably shorter, relative to body size, than those of other great apes. Smaller gut, bigger brain. Cooking is the most plausible reason the trade-off became survivable at all. Chewing time backs this up from a completely different angle. Modern research led by biological anthropologists Catherine Zink and Daniel Lieberman measured how much less effort it takes to chew cooked food compared to raw food, even when the raw food was already sliced or pounded first. Cooking alone cut chewing effort dramatically. Less time spent chewing meant more time and energy available for literally everything else. Moving, socializing, thinking, surviving. If this part surprised you, that cooking may be one of the single biggest reasons the human brain got as large as it did. Sit with that for a second. Because it means something as simple as digging a scorched root out of warm ash may have quietly reshaped the entire trajectory of human evolution. Safety played a role too, even if early humans had no concept of bacteria or toxins. Many wild roots and tubers carry natural compounds that irritate the digestive system or block nutrient absorption when eaten raw. Heat neutralizes a large share of these compounds. Groups that happen to eat more cooked plant food, even accidentally, likely suffered less digestive illness and absorbed more real nutrition, without ever understanding why. Natural selection doesn't require understanding. It only requires an advantage that keeps showing up generation after generation. Once groups understood that fire consistently improved plant food, applying the same idea to properly hunted meat was a short, logical step. A man who had just killed an animal himself, following the same practices his group always used, could now bring that meat close to a maintained flame instead of eating it raw on the spot. The improvement was the same one he'd already seen with roots and tubers. Softer texture, easier chewing, a smell that made the meat more appealing rather than less. There's a physical detail about early plant foraging near burned ground that rarely gets mentioned. Not every root or tuber caught in a wildfire ends up evenly cooked. Some are charred to the point of being inedible. Others are only partially exposed, cooked on one side and still raw and starky on the other. Early humans experimenting with this food source had to learn, through direct trial, which parts were genuinely improved by fire, and which were simply ruined, a messy process with no guarantee that any two burned patches offered the same experience twice. Smell almost certainly played a bigger role in this discovery than most people assume. Roasted roots and scorched seeds produce a strong, distinct aroma that raw versions don't, caused by chemical reactions in starch and plant sugars exposed to high heat. That smell could travel a real distance, meaning early humans didn't necessarily need to witness the aftermath of a fire directly. They may have simply followed a scent they'd never encountered before, arriving at a burned area purely out of curiosity about where that unfamiliar, appealing smell was coming from. Texture change mattered just as much as taste, and for a species without cooking tools of any kind, this had immediate practical consequences. Tough raw roots and fibrous raw plants require significant bite force and prolonged chewing to break down. Early human jaws and teeth, while more powerful than modern human jaws, still had real physical limits. Cooked food requiring dramatically less mechanical effort to consume meant a wider range of individuals, including those with worn or damaged teeth, could access the same food source effectively. An older individual with compromised teeth suddenly had a genuine dietary option that raw roots never offered as easily. Children likely benefited even more directly from this shift than adults did. A young child's jaw and teeth are far less developed, and tough raw roots or fibrous raw plants present a genuinely harder mechanical challenge for a smaller mouth to process. Softer, cooked food would have been dramatically easier for children to eat successfully, potentially reducing choking risk and improving how much usable nutrition a young, still growing body could actually extract from each meal. Social behavior around food likely shifted once cooking became regular practice, connecting to some of the biggest theories about human social development. Maintaining a fire requires someone to tend it, feed it, and protect it, activities that naturally draw people into a shared space for extended periods. Some researchers studying the origins of human social structure argue that fire itself, more than any single food source, may have created one of the first reliable reasons for a group to gather in the same place at the same time daily, well before language or complex tool use existed in anything like their modern forms. This is likely why cooking eventually became something groups actively controlled, rather than simply stumbled into. Once a group noticed that fire-touched food consistently outperformed raw food, protecting a natural flame, feeding it, keeping embers alive between locations, would have become an obvious priority, worth real effort and real risk to maintain. Evidence from Gesher Binat Yaakov, an ancient site in what is now, shows repeated fire use dating back roughly 790,000 years, with burned material appearing across multiple layers rather than a single isolated event. That pattern matters. A single burn layer could be an accident. Repeated burn layers across a long span of time suggest a group actively working to keep fire present in their lives, not just occasionally benefiting from one that happened to pass through. Not every early human group had equal access to this advantage. Groups in regions with frequent natural fires, dry grasslands, lightning-prone seasons, had far more chance to encounter cooked food accidentally than groups in consistently wet, fire-resistant environments. This means the path toward controlled fire use may not have unfolded evenly across the species, with some populations gaining the nutritional and safety benefits of cooking long before others ever had the chance to notice it. Preservation added another practical advantage that likely reinforced the habit once fire became more reliably available. Lightly smoking or drying properly hunted meat over a low, sustained flame slows bacterial growth compared to raw meat left exposed in open air. A group with consistent fire access could stretch a single successful, properly conducted hunt across several extra days, rather than racing to consume or lose it before it spoiled. A real advantage layered on top of cooking's more immediate digestive and safety benefits. There's one more detail worth mentioning before we close this out. The ability to reliably create fire on demand, rather than simply maintain one that already existed, came far later than the ability to use fire at all. For an enormous stretch of human history, cooking depended entirely on keeping something alive rather than making something new, which means every single meal cooked over an unbroken flame represented a genuine, ongoing act of care. Not a simple flick of a switch the way it is today. So the next time you casually toss something into a hot pan without a second thought, remember that this exact transformation, heat turning raw material into something softer, safer, and more nutritious, was likely stumbled into by accident, in the warm ash of a wildfire nobody controlled, by someone hungry enough to dig out a root that looked ruined. What became one of the most defining habits in human history may have started as nothing more than desperation meeting opportunity in exactly the right place, at exactly the right moment.